Hello, my name is Lucas Ravens, and this is drone-based citizen science for monitoring coastal hazards throughout the Great Lakes of North America, which is a project myself, Dr. Tierkoff, Dr. Bunting, and Dr. Mack have been working on through Michigan State University. Documenting coastal impacts are the foundation of data-driven coastline management practices. By understanding the location and magnitude of impacts, managers can evaluate what sort of shoreline mitigation and adaptation strategies are appropriate for specific areas of the beach. This is especially relevant right now due to the current extreme high lake levels threatening coastal communities. You can see an example of this here with the house that is about to fall into the lake. Recently, drones have become a popular low-cost survey method to document these changes, as they can generate extremely high-resolution aerial imagery of the coastline. Then, through specialized photogrammetry software, this drone imagery can be used to generate large-scale data products like orthomosaics and elevation models. While there are many examples of drones being used for coastal monitoring, they have virtually never been used in conjunction with citizen science. For example, by utilizing community members as drone pilots surveying beaches within their own areas. By having citizen scientists as the drone pilots, you are able to achieve a much broader geographic monitoring ability than you would with a traditional research team, as well as the ability to take a rapid repeat imagery, which is especially important when trying to monitor the effects of sudden, unpredictable events like storms. For instance, if you have geographically dispersed field sites around Lake Michigan, a single research team might not have time to survey any of them between the time a storm is forecast and the time it occurs. It might then realistically take several weeks for the team to get out and visit each site after the fact. However, if you have trained citizen scientists ready and able to collect imagery within their community at a moment's notice, we were able to simultaneously survey all sites shortly before and after the storm, as you can see from the bottom portion of this hypothetical timeline, giving you much more relevant and timely data. So to investigate this potential for utilizing citizen scientists as drone pilots, we have established the Interdisciplinary Citizen-Based Coastal Remote Sensing for Adaptive Management Program, or ICECREAM for short. This is a pilot project through the NSF Coastlines and People Initiative that sets up a network of citizen scientists utilizing drones to monitor coastlines in the Great Lakes. The basic workflow of this project is that we identify coastal communities and establish a program in each one by putting on a workshop where we can identify potential citizen scientist pilots and gather baseline data about coastal hazards they are experiencing. We then spend time training the pilots to collect imagery, which we aggregate and generate data products from. We then return these data products to the communities to be used for coastal management. For this initial pilot project, we are aiming to establish citizens flying in 6 communities around the Great Lakes. We currently have pilots established and flying in 2 of them, Manistee and Marquette, with 4 more in development. So to prepare these citizen scientists to collect imagery, we provide them with all the hardware they need to fly. This includes the actual drone, extra batteries, and an iPad controller. But before they're ready to fly, we provide them with all the training materials and funding for citizens to get certified as remote pilots through the FAA. We then provide actual hands-on training in drone operations. And usually the way this works is for their first time collecting data, we will be out there in the field with them. For their first flight, we are the ones controlling the drone, showing them how the operations actually work. Then, for the second flight, we both fly, allowing them to take supervised control of the drone. Then for the third flight, we let them take full control and make sure they feel comfortable flying solo. We also provide them with all of the pre-planned missions and settings already set up on their iPad, with the idea being that the drone operations and mission planning are really plug and play for the citizen scientists. Unfortunately, because of COVID-19 restrictions, some of this training and troubleshooting has had to be through Zoom, as you can see in the photo, but we have continued training pilots nonetheless. And coordinating where and when the citizen scientists fly is a big part of the project. For the where, we select sites based on susceptibility to shoreline changes, which are determined through our own field surveys, as well as which sites are of greatest concern to the community. This is information that we get through a mapping activity conducted through the initial community workshop. For this mapping activity, we give participants a blank map and allow them to highlight areas of concern for coastal management on the map. For the when, we monitor weather patterns and contact citizen scientists to fly before and after storms that might cause shoreline change. We can also coordinate to fly around shoreline modification to track the effects of things like seawalls. Once the sites have been selected and the pilots have aggregated imagery, we have set up an online portal for citizens to upload their imagery to. We then download this imagery and generate usable data products like orthomosaics and elevation models using a photogrammetry software like Agisoft Metashape. A crucial step in generating these data products is georeferencing them through the use of ground control points. These ground control points are objects in a given site, for instance, a fence post or a structure on the beach that does not move and is visible in the drone photos. For each one of these objects, we record their location with a high accuracy GPS, which you can see in the two photos to the left. We then identify these photos and reference the data products to a coordinate system in the real world. In some areas where there are no identifiable structures on the beach that can be used as ground control points, we have to put in our own. And people have come up with many different designs for these artificial ground control points, but we settled on a design you can see on the right, which is basically a long pipe with a high visibility white plate on the top that we pound into the ground at our sites. So our initial results to this project are extremely encouraging. We have found that with basic training, these citizens are able to collect research grade data with less than 5 centimeter resolution, which is extremely high, especially compared to other sources of imagery like satellites. You can see how much this sort of resolution allows you to see in the photo to the left, which is a zoom in of a man on a tailgate, which in this case, I believe is actually the citizen scientist pilot. And if done correctly, these data products can have less than 10 centimeter accuracy, which we evaluate using something called called checkpoints. These are the same as ground control points previously described, but are not used to reference the image, but instead used after the fact to evaluate the accuracy of the image. In the scene to the upper right, you can see we have 5 ground control points in green and 3 checkpoints in blue. And based on these 3 checkpoints on the table to the bottom right, it looks like we have a total area error of around 5 centimeters, which is basically as good as it gets. That's really impressive. So using this imagery, we have been able to observe and model some pretty drastic shoreline changes that have recently occurred. This is a very popular walking path at one of our sites that has been destroyed by wave energy in several places. These 3 images are all showing the same area outlined in red. The upper right being the orthomosaic generated from the drone images, and the lower right being an elevation model we can use to quantify how much sediment has been lost. Especially with the current high lake levels we are experiencing, this sort of thing is not at all uncommon. And here is a site on Lake Superior that has also experienced a good deal of erosion. These are 2 flights conducted 5 months apart. The upper images were taken in late June, and the lower images taken in late November. And it's hard to see the erosion from the whole images to the right, but if you look closely at the area outlined in red to the left, you can see the results of these coastal changes. For example, the red and white beach stand in the upper left image has been totally washed away, and the concrete debris on the beach has been completely exposed. In this same spot, we can actually quantify the erosion that has happened with the data products we have generated. The red and blue area in the upper right is what we call a subtraction map, which is basically the difference between the 2 elevation models generated on the 2 different dates. From this map, we can see that the greatest shoreline loss has been in the right side of the area. And over the whole scene, this loss is equal to roughly 450 cubic meters, or roughly 40 dump trucks worth of sand lost in just under 5 months, which is not at all insignificant. On the bottom, I have digitized the erosion lines of each of these areas, and we can see that in some areas we have lost over 3 meters of shoreline in this short time period, which goes to show just how fast the changes are happening. So this is an ongoing project, but we have learned several important lessons from our initial results. We have found how important it is to select qualified and invested citizen scientists as pilots. For example, one of our pilots experienced a malfunction with the altimeter of her drone, which led to the imagery of a few flights being unusable, which you can see in the top two images. The left being a good flight, and the right being completely warped and unusable. The pilot who took these images was great and was willing to spend time with us troubleshooting the problem, but someone who wasn't as invested in the program might not have been willing to put in the time to make sure everything is working properly. Also, a lot of care and thought needs to be put into the distribution and type of objects used for ground control points. In areas where we have had to install our own ground control points, we have found that getting permission from land managers to put in these points takes a lot of coordination. Additionally, we have had problems with losing ground control points at our sites. At one site, you can see in the bottom, we've actually lost half of our initial points due to erosion in the 6 months since we put them in, which just goes to show the magnitude and speed at which these changes are happening and how important it is to document them, allowing coastal managers to make informed, data-driven management decisions. So thank you very much for your interest in our program. I would like to thank our support staff at the Michigan State University Remote Sensing and GIS Department, as well as our citizen scientists, pilots, and community stakeholders. And I look forward to answering your questions. Thank you very much.